Welcome to my demo reel. My name is Guillermo Trejo and I will present 3 projects that I worked on during my studies at LaSalle College Vancouver. Shaman is a third-person action-adventure game created with Unreal Engine 4. The project was developed over a year by a team of 8 persons, 4 programmers and 4 designers, as part of a set of courses to learn the production pipeline of a game. My main role in the project was as a gameplay and AI programmer. One of the key mechanics of the game is that the main character has the ability to transform into a jaguar. My main contribution to the game was the implementation of the jaguar locomotion and combat system. I was also in charge of the shapeshift transition that involved particle effects and, most importantly, the handling of the collision detections for each form of the character. Shaman has 3 types of enemies: the striker, the caster, and the brute. I contribute to the implementation and debugging part of the AI logic for all the enemies. This gave me a deeper understanding on how to work with behavior trees in Unreal Engine 4. I also had the opportunity to create a custom interface using Unreal Data Tables as a tool for game designers to tune the game variables of the main character and enemies, with balancing purposes without touching a single line of code. Shaman is a free experience and ready to download at itch.io. It starts by rendering a single triangle, then 2, then a cube, a sphere, a skydome, an earth, a dog, a bunch of dogs, a skeletal model, and to an infinite options. Memo Engine is a 3D game engine developed from scratch in C++ with a graphic pipeline using DirectX 11. Different GPU shaders were implemented with HLSL to support different texture maps to provide models with high frequency detail, color, and surface. Textures like specular map, displacement map, and normal map. Thanks to the skeletal model implementation, the engine supports loading models with various animations and bone structures. At the same time, the engine has real-time shadow and dynamic lighting. These shaders offer unlimited creativity when loading models, and with post-processing shaders like bloom, gameplay and graphics can reach another level. The physics module of the engine is based on particles with constraints, with Berlin integration for motion. Using tetahedrons to load models and adding collision OBDs, we can have a good sense of what we can achieve with the physics engine during gameplay. The engine is still in development, and one of the latest features of the engine was the terrain generated with a height map image. One of the main goals of the engine is to provide the user with a data-driven component-based architecture loaded through JSON files to create and handle game objects, mixed with different shaders to create appealing gameplay, such as the pixel post-processing, where we can modify the width and height of pixelation, and swirl shader, where we can modify the radius and angle of the effect in real time. Halloween Wars is a multiplayer real-time strategy game made in C++ and based on a game called Galcon. After choosing your favorite type of monster, the objective of the game is to send swarms of monsters from planet to planet to take over the galaxy. Each planet has only one owner, and the number on each planet indicates how many monsters it will take to conquer them. Each planet produces monsters for the player at different production rates. To check this number, just need to hover the mouse over the planet. After selecting the planet with a click, the player can select what percentage of monsters to send with the scroll wheel on the mouse and a right click on the destination planet to initiate the attack. The aim of the game is to defeat the other players by eliminating all the planets. Halloween Wars is a server client game, where the server manages and controls each client's instructions and transmits back to all clients. The challenge developing this game was the multiplayer programming. I created a network library to support it using Win32 sockets. For the monster displacement support, flocking steering behaviors were implemented, and finite state machine supports the animations of monsters and planets. This project gave me a solid understanding on how multiplayer game programming works, how it is implemented, and the challenges that we might encounter, such as lag compensation, replication, client-side prediction, cheating, and management of server performance. Thank you for watching. If you want to see more, don't forget to click on the links.